Assalamualaikum warahmatullahi wabarakatuh, and salam sejahtera to all my students. Okay, for today's lecture, we are going to cover about the migration rates of solute in chromatography. Okay, chromatogram is useful for both qualitative and quantitative analysis. So basically, chromatogram peak will appear uh, on the detector at the instrument such as HPLC, GC, um, and also on the size exclusion chromatography. So we can measure the migration rate of solute by determining the peak at the chromatogram. So the position of peak on the time axis will identify the component of the sample, and the areas under the peak quantitative measure of the amount of each component. So the area below the curve actually measure the amount of component, and the amount of peak it identify what is the component that appeared on the chromatogram. Okay, look at the next slide. Right, this is the chromatogram example of chromatogram detected response as a function of elution time. So this one is the detector responses, and the x-axis is the time. Okay, we can see that the first compound appeared is CH4, and the second component appeared is octane. Third one is unknown, and the fourth one is the no name. Right, so chromatogram will give you where is the retention time, what is the dead time. So it is for dead time, it is illustrated or laminated by symbol TM. And this one is TR, which is the retention time. We can measure the retention time starting from the injection time until the middle of the peak here. Okay, we measure at the middle point here. And this one is the stationary time. Okay. The effectiveness of a chromatographic column in separating two solutes depends in part on the relative rate at which the two species are eluted. So, for you to determine the compound separated, at least you need to have two compounds so that you can make a comparison. So, the effectiveness of the chromatographic column in separating two solute, it depends on the relative rate at which the two species are eluted. So these rates are determined by the magnitude of the equilibrium constant for the reaction by which the solutes distribute themselves between the mobile and the stationary phase. Okay, the distribution equilibria involved in chromatography involve the transfer of an analyte between the mobile and stationary phase. So analyte is the compound that you're going to separate, and actually the equilibrium constant, which is given by the Kc, is given by the formulas Kc equal to Cs over Cm, whereby Cs is the molar concentration of the solute in the stationary phase, and Cm is molar concentration in the mobile phase. And the K is a constant over a wide range of solute concentration. So this equation we are not going to use in the calculation step, just for your general information only. We look at the terms for that time, which is given by Tm, stationary time, which is Ts, and retention time, which is Tr. Okay, the time between the sample injection and the appearance of the non-retained species peak is called as the dead time, or also known as a void time. So you need to know what is the location ataupun the location or the actual position of Tm on the chromatogram, so that you can make a calculation to determine the retention time, to determine the selectivity or the capacity factor, and so on. It is the time it takes for an unretained species to pass through chromatography column. So all components spend the dead time in the mobile phase, and the separation are based on the different time, which is the stationary time that components spend in stationary phase. So the dead time provide a measure of the average rate of migration of a mobile phase and is an important parameter to identifying analyte peaks. So dead time actually it has its own value. Okay, the time it takes after sample injection for the analyte peak to reach the detector is called the retention time, denominated by TR. The analyte has been retained because it spent a time in the stationary phase. So we nominate it as a TS. The retention time is then calculated by, okay, you need to know or familiarize with this formula. So retention time is given by dead time plus stationary time. Okay, if you ask to calculate the retention time TR, it is TM, which is dead time plus stationary time. So make sure you can draw the graph. Okay, so let's practice how to draw the graph. Right, so the TM is we consider from this point to the middle point of the peak here. Okay, and the stationary time from the peak at the end of the melting block that time until the center of the peak of the first peak. Okay, for first component, if you have more than one component, so you can measure the dead time for second component. Okay, so for retention time, starting from the origin until the peak that you want to measure. Okay, I will give you some example. Okay, by look at the data chromatogram here, the question will ask you, please include in your diagram the retention time, dead time, and peak width for all the species, for all the unretained propanol and butanol. Okay, you need to draw the TR, the TM, and also the peak width for all the species. So what you are going to do first, you need to sketch. Sorry. Okay, first you need to draw a line. Sorry, macam mana drawing? Okay, first you need to draw a vertical line here. Right, sorry kalau sengit-sengit sebab saya guna drawing pad, so tak biasa lagi. So, okay, first you need to draw the unretained species. Okay, macam ni. So, and then second one is the propanol. Okay, and the third one is the butanol. Right, and this one is time. Okay. Time in minutes. And this one is detector signal, right? So what you're going to do is you need to label where is the TM, TR, and the peak width, right? So starting from center of the peak, you need to draw. You must draw a straight line because I'm using the drawing pad. Difficult for me. Okay, this one is TM. Okay, and you need to state the value of the peak width. So for TM, there is no peak width value, but the value for the retention time of TM or the compound which is called as unretained is 0.3. This one is the value for unretained. Sorry, 0.3. Okay. Okay. For the second one, here is the propanol. Okay, starting from here to here. is the retention time for the propanol, which is 2.0. This is retention time. You can tulis kat sini TR propanol. Okay, propanol. TR propanol. Okay, this one is the dead time for unretained species, which is 0.3. Okay, and the last one, starting from center. Okay, tak cukup pula, sepatutnya awak kena ke atas sikit lah dia punya detector signal ni. And this one is 4.2. Okay, 4.2. Retention time for butanol. Okay, so peak width, don't forget to draw peak width. Okay, buat macam tu lah. This one is 0.8. Okay, so the measure between these two days is the peak width. This one 0.2. Oh sorry, this one is 0.4. Okay, 0.4. And yang ni tak ada peak width. Okay, macam tu je cara nak lukis dia. Okay. Okay, proceed with our next slide. Okay, retention factor. The retention factor is given or nominated by K prime. Okay, so the other name for retention factor is the capacity factor. It is an important parameter that is widely used to describe the migration rate of solute on columns. For example, for a solute A, okay, the retention factor K prime A is defined as the retention time minus with dead time divided by the dead time. Or you can straightly use Ts over Tm. But basically in the question, they will not give the Ts value. So you need to see the question what types of the value given, whether Tr or Ts. Okay, K prime A is the distribution constant for the species A. Tr and Tm are readily obtained from a chromatogram. And the retention factor Ka or K prime A for solute is related to the rate at which A migrates through a column. It is the amount of time a solute spends in the stationary phase relative to the time it spent in the mobile phase. So ideally, the separation are performed under condition in which retention factor for the solute in a mixture lie in the range 1 to 5. So after you calculate the retention factor, so you can conclude in several ways, whereby when the retention factor value for our solute is much less than this range, which is below 1 to 5, so we can conclude that the separation occurs so rapidly that the accurate determination of the retention time is difficult. For example, if you got the value is 0.5, so it is below 1, so we can conclude that the separation is too fast. Okay, so when the retention factor is larger, which is 20 to 30, the separation time becomes inordinately long, which is it has longer time to separate. Okay, we look at the selectivity factor. Okay, nominated by alpha is given by Kb over Ka. So Kb is the retention factor of species A and K prime A is the retention factor of species B. So we can measure the selectivity factor by using this formula. Okay, value from capacity factor. Okay, awak dapatkan value capacity factor dulu baru boleh awak kira value selectivity factor.